Welcome back to math, and today we're going to be finding vertical asymptotes and discontinuities. This word right here means a hole. So that big word discontinuity just means hole. Kind of keep that in mind. So you've talked about discontinuity or their asymptotes before. You've talked about asymptotes. You have an idea of what they are. We've looked at horizontal asymptotes. But holes and discontinuities may be new for you. So we're going to spend some time kind of looking between the two. What's the difference between them? So first, a vertical asymptote and a discontinuity or hole are both gaps in the domain of a rational function. So that means that they're excluded x values. So that means there's some x value or x values that if you try to plot them on the graph, there's actually no y value that goes with it. You actually can't have that x value on the graph at all. A discontinuity, though, is removable. We'll look at what that means. While an asymptote is not without changing the entire look of the function. So we're going to start with these two examples. First one on the left, the graph below has a vertical asymptote at -5. And that, I mean, that's kind of obvious, right? So there's this invisible barrier that the graph kind of skims. It kind of curves around it. It doesn't want to touch it. It doesn't want to cross it. You can see it there. It's your asymptote. And by the way, if you remember in the horizontal asymptote video, that some graphs don't have horizontal asymptotes. They actually have slant asymptotes. This is one of those. We don't have to worry about it right now, but that's going to be your slant asymptote right there. But in any case, I've got a vertical asymptote. Kind of obvious, easy to see. And this, by the way, is this equation right here. Go ahead and just jot it down because I forgot to print it on the paper before I copied them. So this is this equation right here. This one, on the other hand, here's the equation. So here's the equation for this one. Let's call it g of x because why not? Here's this equation. Now, this looks like it should be a rational function, okay? Because it's in a fraction form. It's kind of looks like that one. I mean, the only difference between them is this has a -25 in the numerator, but otherwise they both got an x squared and they're both divided by x plus 5. So they look like they should be about the same graph, and yet this one looks like a line. So what's wrong with this one? So apparently I'm telling you this graph has a hole at -5. Let's go over to Desmos and see just what the heck that means. I've already typed in the equations for you. Here's the one. So the orange one here is the one that's on the left on your paper. It's a rational function. It looks like a rational function. It's got that vertical asymptote right here. It's got a slant asymptote. And the equation is in the form of a fraction. So it's kind of what we expect it to look like. Now here, let me just kind of hide that one. Here's the one that's on the right. The equation looks like a fraction, and yet when you look at the graph, it's just a straight line. And then on your notes, I told you that there is a hole at -5. So what does that mean? I don't see a hole here. Do you see a hole here? Looks like a solid line to me. So what I want you to do is either watch or graph this on your own, and you're going to use just the mouse on Desmos and go to where x is -5 and see what happens. Okay, so when I hover my mouse over -5 on this graph, it doesn't give me a y value. It says that the graph is undefined at -5. That's what a hole is. It means that if you try to put -5 in for x, you're not going to get a value out of it. So, and on a calculator, it will show as undefined. But notice that I did not see this on the graph until I knew to look for it. So what we're going to be doing now is looking at how do you tell if there's a hole on your graph that you can't see unless you know where to look. Asymptotes are easy. So let me go back to the asymptote. Asymptotes are easy. Like they're right there. There it is. Bam. You can see it. You can almost see that line there even without drawing it. The hole is completely invisible until you go to it and click on it. So let me head back to my paper here. So we know we have a hole at -5, and we know that when we got to the point -5, the graph in fact showed us an open circle, and the point was listed as -5 undefined. That means there's no y value there. It means that point doesn't actually exist, even though the graph shows you a solid line. So why doesn't it exist? We're going to plug this into the equation. So I have my equation here. I'm going to plug -5 in for x. So I'm going to get -5 squared minus 25 over -5 plus 5. Let's simplify that. Let's see what we get. So -5 squared is 25. 25 minus 25 is 0. And of course, -5 plus 5 is 0. Now remember, I can't have a 0 in my denominator. You learned that way back in, I don't know, elementary school probably. Oh my God, I can't do that. Okay, so definitely there's something wrong with that graph there. But notice here I also have a 0 on top. If I do the same thing here on the left where I've got an asymptote at -5, so same number, but let's see what the result is. So I'm going to plug -5 into this one now. So -5 squared over -5 plus 5. -5 squared is 25. -5 plus 5 is 0. So this is the difference that we're going to be looking for. We're going to find out where the denominators equal 0, because that's my excluded values. That's where the graph cannot exist. So I can't have a 0 in the denominator, so that's where the graph won't exist. And then if I plug in that number and I get a 0, then I know I really have a hidden hole on my graph somewhere that my calculator's not going to show me unless I know exactly where to look for it. If I end up with some other number on top, then I know I've just got an asymptote, and you can probably see it in the graph already and not even have to have gone through this. So let's go ahead and try some. Let's open this up. And I've got some steps for you here, but it always kind of amounts to the same thing. Find out where your denominator equals 0, then plug the number back in and see if you get 0 on top or something else on top. I'm going to actually go ahead and graph this first so that we can get some idea of what we're going to look for. All right, so here we go. I've got my graph here in Desmos. It's in a fraction form, and yet it doesn't look like a rational function. It just looks like a line. So I'm kind of thinking that I'm going to have a hidden hole here someplace. I just have to figure out where it is. So, and I don't see any asymptotes. In fact, you can zoom out a little bit if you want to. There's no asymptotes on this graph at all. It just looks like a straight line. It looks normal, but it's not normal. It's tricking you. Don't let it fool you. Let's go back to the paper. So let's find out. Let's see where this hole is hiding that we think is there. So the first thing I want to do is set my denominator equal to 0 and solve using any method. So basically, I just want to see where x minus 3 equals 0. What values will make this 0? So take your denominator, make it equal 0. Now this one is super easy to solve. Just add 3 to both sides and then you'll be done. So x equals 3. So that means when x is 3, then my denominator will be 0. And of course it will. 3 minus 3 is 0. This makes my denominator equals 0, which is not allowed. I cannot have a 0 in a denominator until you get to calculus class, but we're not there yet. So these x values are either vertical asymptotes or discontinuities, as we were discussing. Now, we looked at the graph. It didn't have any asymptotes, so it probably has a hole, and we need to just confirm that that's what's happening. To find out which, plug them into the numerator and simplify. So I'm going to take 3, and I'm going to plug it into my equation. So x squared, so 3 squared, minus 2 times x, so 2 times 3, and then minus 3. And then, so x minus 3, 3 minus 3. Okay. So denominator 3 minus 3, we know that's 0. That's how we found 3 in the first place. But on top, so 3 squared is 9, minus 6, minus 3, that also comes out to 0. So I have 0 over 0. So did I get 0? Yes, I did. And remember, so 0 over 0, oh my God! Whenever you see 0 over 0 and you've plugged your number in, that means that's a hole. That's a discontinuity. So yes, since I got 0 over 0, x equals 3 is a hole or discontinuity in the graph. If I had not gotten 0, then I would have an asymptote, but I would have seen that on the graph. So I was already pretty sure that wouldn't be it. So yes, x equals 3 is a hole in the graph. So now let's do a little sketch, and let's go back to Desmos and look at it. So I'm going to look at Desmos at where x equals 3 and see if it gives me that hole again. Let me zoom back in. Okay, 3, there we go. Ooh, there it was. It's hard to focus on it. Okay, so notice when x is 3, y is undefined. And notice the dot. So normally my dot is solid, yet when I get to 3, I can land on it again. There. It's an open circle. That means it's a hole. It even looks like a little hole in the line. It's not normally going to be visible to you. You have to know where to look for it. But it is there. Once you know it's there, and once you click on it, Desmos will show it to you. I believe the Inspire will as well. It's just a little harder to work with. So I just do a little sketch. There's my hole at 3, comma, undefined. So there's my hole in the graph. I want to skip to number 4 together. We will look at these in class. We're going to look at number 4 right now. So I've already got this graphed in Desmos. I encourage you to always look at a graph of these functions first to give yourself an idea of what to look for. So here we go. Here's my graph. Now I see a very obvious vertical asymptote. I also see a horizontal one, but I don't care about that right now. So just leave them alone. We're not going to worry about it right now. But I do see a very obvious vertical asymptote. So I know I'm probably going to have a vertical asymptote at -1. However, again, if there's a hole here someplace, the graph is not going to show it unless we know where to look. So we need to first figure out, where do I look? Let's see if we can work that out. So my first step, let me switch back. My first step, set the denominator equal to 0 and solve using any method. So that means I'm going to take just this guy, -4x squared minus 16x minus 12, and I want to see where it equals 0. Now, you could factor it, you could and solve it, but please don't. Or you could graph it, and I suspect most of you will be graphing to solve this, so let me do it that way as well. So I have, in fact, I'm just going to copy and paste. In fact, will Desmos solve that for me? Yeah, okay, yeah, it does. So Desmos will solve it for you. But if you want to do this by graphing, so I want to see, here's my denominator, just the denominator all by itself, and it equals 0 at -3 and -1. So that means when I plug either -3 or -1 in for x, my denominator is going to be 0. And as we know, you can't have 0 in your denominators. So that means my excluded values are -3 and -1. So let me switch and write that down first. So x equals -3 or x equals -1 are excluded values. So if I plug either of these into the denominator, I will get 0 and something on top. And I can't have 0 in my denominator. So now I need to test these. I need to see, are they asymptotes or are they holes? Now we already know that x equals -1 is an asymptote. Let me go back. You can go away. So I'm already pretty sure that here at -1, that's an asymptote. It looks like one. Like, it's obvious. It's in your face. And I'm kind of suspecting that -3 is going to be a hole. In fact, let me just try it right now. Yep. Oh, hey, I landed right on it, and then I lost it. Come back. Where are you? Okay, there. So -3 is a hole. -1 is an asymptote. So there's that undefined part. And there's, again, that hole you wouldn't see unless you knew where to look for it. So let's go back. I know that this is an asymptote because I can see it on the graph. And then I just checked, and it looks like this is a whole, or a discontinuity. So I do want to confirm that numerically, though. Let's go ahead and do this step. We're going to plug both of the values into the original function right here and see what we get. So let me just test my whole first. I have -3 squared minus 3 minus 6 over -4 times -3 squared minus 16 times -3 minus 12. And I get, let's see, 9 minus 3 minus 6 is 0. Okay, and there it is already. So remember, 0 over 0 means you have a whole, because I know that's going to be 0. Okay, so 0 over 0 means whole. Asymptote means some other number over 0. So let's try it. So I have -1, so -1 squared plus -1 minus 6 over the denominator, which I already know is going to come out to 0, because that's how I found -1 in the first place. I'm running out of room to write, you guys. This isn't good. All right, 0. Okay, so -1 squared is 1, minus 1 is 0, minus 6 is -6. So a number other than 0 over 0 means you have an asymptote, or you can see it in the darn graph. And 0 over 0 means you have a whole. And again, you can check that on your graph as soon as you know where to look for it. So we're going to go ahead and try these in class together as kind of a warm-up check, and then you'll have an assignment to work on. Thank you very much.